So let's now move on to further topics, which is going to be about the physical properties of alkanes, right? So what could be said there? So the CH bond in alkanes is considered nonpolar because the electronegativity values of the carbon and hydrogen are very close to one another. Even though they're different technically, right? Once you take a look at the periodic table, you can see that, okay, well, these are distinct elements. They are at a particular distance from one another, and that they're not quite close to one another, like in the periodic table, which signifies that they will have different electronegativities, right? So, but if we look at the values, if we look at further data, turns out that their values of electronegativities are very close to one another. That's why it was kind of like agreed upon that the CH bond is non-polar, because electronegativity values of the C and H are very close, right? So to the point that it's considered, it's kind of postulated to be non-polar bond, right? Which lends various properties to alkenes, such as they are non-polar molecules overall. So because you'll have nothing more than the combination of the carbon-carbon bonds, right, in your typical alkane, which is going to be looking like this, right? So, and you will have the CH bonds, right? So you have CC bonds, which are like identical carbon-wise to one another. So they are definitely non-polar. Then you have CH bonds, which are also considered non-polar, even though they consist of two different atoms, right? Oops, I made a mistake here. Too many H's, right? So it's going to be CH3, CH2, CH3, right? So then since you have non-polar bonds only, this is like overall a non-polar compound. The alkenes are non-polar. So that means that they are not soluble in water because water is a polar solvent, right? So it was determined experimentally that their density is less than the water. So, and also it was determined experimentally that the higher the molar mass of the alkene, the higher the boiling point will be, because typically heavier compounds in terms of their molecular weight will have a higher boiling point, right? So basically it will take like more temperature, higher temperature to evaporate a compound with a higher molecular weight. So then moving on, so what else do we have here? So we have the notion of polarizability, so to speak, that is about how easy it is to shift or generate the partial charges on a particular alkane, right? So what do we mean by that? So here we have the example of two alkanes, right? Let's say one of them is going to be propane, by the way, right? So now we can use our newly minted knowledge of nomenclature rules. So here we go. This is going to be an alkane, CH3, CH2, and another CH3, right? Versus, let's say, a molecule of butane, right? So molecule of butane. So this is gonna be about the generation of dispersion interactions via polarizability and the impact of those things on the boiling point of the propane versus butane, right? So let's take a look at those examples here. So here we go. So these are our molecules of interest. So they will have drastically different boiling point, minus 89 degrees Celsius versus minus 42 degrees Celsius. So this is going to be a much higher boiling point compared with this one, right? So minus 42 is less negative. It's closer to zero, closer to like positive boiling points, consequently temperature-wise, right? So then minus 42 is much higher than minus 89 Celsius, even though they're both negative temperatures, technically, right? So, but turns out that if you have a higher molecular weight alkane, it will have more dispersion interactions, right? Which will be characterized by the generation of a larger number of temporary positive and negative charges, right? So here, for example, you can generate the positive and negative charges across a 3-carbon chain, right? There's going to be a particular number of positive and negative charges that will lead to the dispersion interactions, right? Between the, let's say, several molecules of propane, right? So here you have a longer chain, right? So you have more carbons, and consequently, you'll be able to generate more number-wise temporary positive and negative charges, which will lead to the stronger interactions between the molecules of butane in this case. Consequently, if we have stronger interactions between the two molecules, it will take higher temperature to separate them, right? So that's why the boiling point of this longer chain alkane is higher than the boiling point of the shorter chain alkane. If you think about, let's say, maybe decane, it will conceivably even have an even higher boiling point, right? So then let's say pentane, right, for example, or butane in our case. So then if you look at the notion of branchedness, so branchedness will also impact the boiling points. Let's take a look at our, again, couple examples, which we'll see in our slides. That's going to be our pentane, which is going to be looking like this. I'm going to specifically show the carbon skeleton drawing here, which is going to be looking like this. And this will also force you to practice the carbon skeleton drawings, right, on your own. So then we're going to compare, we're going to note its boiling point, 36 degrees Celsius, versus the boiling point of the branched alkane, right, such as this one. So I'm going to show the isomer, by the way, speaking of, again, newly acquired terms, that's going to be the isomer alkane, right? So, which also consists of the same number of carbons and hydrogens, right? Just like this one. So here you have 1, 2, 3, 4, 5. 5 carbons in this particular hydrocarbon. So then you have the respective number of hydrogens, right, which you can also like add here. And then what you're going to realize is that it turns out the boiling point is much different, right? So much lower, minus 9.5 degrees Celsius compared to this. So 36 is much higher than minus 9.5. Why is that so? Because it turns out these two molecules can be tightly packed to one another, right? Because of their linear structure. Consequently, it's going to be harder to separate them if they're closer physically to one another. The branched molecules are physically kind of much more distant from one another. If we draw them together, right, then we'll see that the distance between the molecules will be much farther compared with this distance. So consequently, they will be easier to separate. It will be easier to separate those two molecules because they have a higher distance between one another due to the branchedness that kind of like repels them, right, from one another. Consequently, it's going to be it will require a much lower temperature to boil this molecule, and consequently, it will have a much lower boiling point than a linear analog, right? Linear isomer, by the way. So yeah, here we have 5 carbons everywhere and the same number of H's if you count them, right? So moving on, it's the notion of miscibility, right? So since alkanes are considered nonpolar compound, they will not be miscible with the polar solvent, such as, guess what? Water, right? Water is a polar solvent, as we know from our general chemistry background, and also we have the notion like dissolves like. So if we think about the salts that are polar compounds, they are dissolving. They can be dissolved in the polar solvents, such as water. Alkanes are non-polar compounds, so consequently they cannot be dissolved in the water, and that's what that was also determined experimentally while people trying to like mix alkanes in water, right? And then turns out they just become like, two separate layers, right? Once you try to mix, let's say, decane in water, right? Let's imagine you're going to mix those two compounds, and then in a beaker of some sort, they will just give you 2 separate layers, right? You'll have the layer 1 here and layer 2. So on the top here, in this kind of like a darker layer with the crosses, you are going to have your decane compound because it is going to be most likely having lower density than water, right? And then here on the bottom, you'll have the water. So whatever compound has the higher density will sink. Whatever compound has lower density will float, provided those two compounds are not miscible. If they're miscible, it's a different talk, right? So they will make a solution, right? So, but in this case, if we try to mix alkane and water will have the immiscible mixture, so they will not be miscible with one another, they will not make a solution, they will just make two layers. And then of course some alkanes can potentially be like with a huge molecular weight, especially, all right, so they conceivably can have a higher density than the water. So in that case, they will sink if this is the case, right? So if the alkane has a lower density than the water, then it will float, right? So that's just going to be like a rule from physics if we recall that. However, with the introduction of the functional groups, right, such as alcohol, we can achieve the miscibility of our organic compound in water, right? So for example, if we take a look at, let's say, the two examples, right? So such as, for example, I don't know, let's take a look at ethane, right? So which is going to be CH3CH3 versus substituted ethane. So now we're going to switch one of the H's to the OH, right? And then essentially we are going to build nothing more than an alcohol, right? So because now we have this COH piece in our molecule of the alcohol or the alcohol functional group. So this will lend to this molecule a polar group, right? So because OH bonds are polar, so consequently we are going to have to speculate that this molecule will likely be soluble in water because it has more similarity structurally to the water molecule. If you recall, the water molecule literally has OH groups in its structure, right? Even like two OH groups. So this molecule is very dissimilar to the water. This molecule is more similar to the water. Consequently, following the principle like dissolves like, we can conclude that this alcohol will likely be soluble in the water. Of course, the experiment will be able to confirm it or disconfirm it. So, but experimentally, it turns out those two compounds are very much soluble with one another, right? And then basically this alcohol is soluble in water. That is confirmed experimentally. So the more functional groups of the, like, let's say OH kind we have, the more solubility in the water we're going to have. Maybe let's say we're going to move on to compound like this, right? Now, so in this case, we're going to have two OH groups, and then if we imagine some sort of like a long chain alkane consisting of 9 carbons with 3 OH groups. So we are going to speculate that this compound will have a progressively higher solubility in the water because it looks more like water and will be able to make more bonds that will lead to the formation of the solution between this compound, for example, with a bunch of OH groups, right, and water. So then moving on, so it's going to be what else? So it's going to be just about the kind of like amount of non-polar and polar character in the molecule, right? Sometimes even if you have the polar group in your molecule, such as maybe it's going to be, let's say, OH group, right? Let's say you have the OH group. So it's just one OH group, let's imagine, right? But you have a huge carbon chain, right? Which consists of whatever number of carbons we're going to show here, right? So this is going to be overwhelmingly non-polar molecule. Consequently, it's going to be like very low chance that this molecule will be soluble in the water. However, if we have the kind of like molecule like that, maybe, so let's show it like this, right? So maybe we have just 4 carbons, right? Or let's make it like 5 carbons in a chain, right? And we're going to have 1, 2, and we're going to have 2 OH groups, right? So now the ratio of polar groups to non-polar groups, right, or polar character to non-polar character is going to be much better, right, than in the previously drawn molecule. So consequently, we can speculate that this molecule will have a higher chance, will have quite a high chance to be soluble in the water, right? So and then if we add even more OH groups, we can speculate that this compound now will have an even higher chance to be soluble in the water compared with the analog of this compound with only 2 OH groups or only 1 OH group, right? So it's going to be just about the balance between the polar and non-polar characters in the molecule that will give you thoughts about the solubility of this particular molecule in water. So last but not least, chemical reactions. So like we are literally going to have to look at only like one major property of alkanes, which is going to be their oxidation, right? Or the burning, combustion of alkanes. So basically, if we start with some sort of hydrocarbon in general, once we combust it, right? So burn it, oxidize it with oxygen, we're going to have the same mixture of compounds as our products. It's going to be CO2 and H2O, right? So then the heat will be released as well as a result of this chemical reaction. So that's why to burn hydrocarbons can be useful to obtain heat, right? So and then use that heat as some form of energy, right? So what we're going to do is take a look at some examples, right? So how the combustion works, right? So we can start with CH4, right? So CH4 is our hydrocarbon. In this case, it is an alkane. We're going to have the combustion of alkanes. The same going to be true product-wise for alkenes and alkynes. They're all hydrocarbons, by the way, right? So only carbons and H's are in the molecules of hydrocarbons. So then we're going to plus O2. So as a reminder, on the left side, we are going to have our reactants. On the right side, we'll have our products. So then this will be converted to what? CO2 and H2O. CO2 and H2O will be the result, right? So then we're going to balance this reaction by inspection, right? So we're going to make sure that we have the same number of atoms of a particular kind on the left and right side. Right now, this equation is not balanced because we have different number of oxygens, for example, right? 3 oxygens versus 2, so not good. We're going to balance it, right? So, but we have the same number of carbons, so that's a good start. So let's take a look at this, right? So we have here more oxygens. So let's make it, here we have 2 oxygens, right? So here we can do the following. What if we put 2 here? We are going to balance our equations with whole numbers, right? So let's make it 4, right? So now we can work with this, right? And then bring it up to 4 as well. So we have 2 oxygens here, only 1 here. Let's multiply this molecule by 2, and then we'll have 2 molecules of water, right? 2H2O. So this will bring us to 4 oxygens on the left side and 4 oxygens on the left side as well. We have carbon-carbon, and we also have how many? We have 4 H's and 4 H's total. So now this equation is balanced by inspection, right? And then we just achieve the same number of each element on the left and the right side, the same number of atoms of each element on the left and right side. So now let's move on to some other examples, right? So if we have a look at some heavier hydrocarbons such as C4H10. So who is that? This is nothing more than our friend butane, right? So plus O2. So again, products are the same. So just like with the case of methane, right? Same product, CO2 plus H2O. The only difference will be, of course, the starting material, right? So the oxygen will be oxygen everywhere. So for the combustion reaction, and then we're going to balance it differently, obviously, right? So here we go, right? So this is going to be a little bit difficult, a little bit different, right? So we're going to have 10 H's here, and then we're going to have also how many? We're going to have 2 H's here, right? So let's take a look at what can take place. So basically, what's going to happen is that we have 4 H's, 4 carbons on the left, only 1 carbon on the right. So let's make it 4 here, right? So then we can change the numbers if we end up having fractions, right? So for our coefficients. So then coefficients, the chemical coefficient, this is something that we can put down ourselves when we balance the equation. Those subscripts are fixed. They signify the particular formula of a specific compound, and they cannot be changed at will. But stoichiometric coefficients follow. They appear before the formula of the compound, and they can be changed dependent on the chemical reaction, which we need to balance, right? So then what else do we have? We have 4 and 4 carbon-wise, right? So then we are going to have 10 H's And now if we make it 5 H2Os, right, then we're going to have 10 H's as well. So that's getting better. So now, next point. So what else do we need to balance? Let's balance oxygens, right? So here looks like we have 4 by 2, 8 plus 5. That's gonna be what? 8 plus 5 gives us 13 oxygens, right? 8 plus 5, 13 oxygens. Here we have 2 oxygens. So theoretically, we can multiply it by 6.5, right? And then now we have all of a sudden 13 oxygens. It's all balanced, but we agreed that we are going to have only whole numbers, right? So at this point it's balanced, but this number is not whole. How can you make it whole? Let's multiply everything by 2. And then we're going to have the minimal possible whole numbers to balance this chemical reaction. So if we multiply everything by 2, not by 10, right? 10 will be an overkill because we have not minimal, but like higher than minimal possible whole numbers to balance this equation. So if we multiply everything by 2, we're going to have put 2 here. So instead of, let me erase it, instead of 6.5, we're going to have 2 here. Instead of 4, we are going to have 8, right? And then instead of 5, we are going to have 10. So now if you count the numbers of each element, right, on each side, it's going to be the same, right? So here you have, for example, 2 by 4, 8 carbons. 8 carbons, 8 multiplied by 1, right? So only 1 carbon in this molecule. So then it's going to be just like in mathematics, right? You multiply the entire compound by the stoichiometric coefficient and you count how many atoms of each kind you have. So then what else do you have here? So you have 8 carbons, right? So you have, for example, a total of 20 H's. So you have here 20 H's, 10 by 2, 20, right? So now you have how many oxygens? 2 multiplied by 10, 20. No, sorry, oxygens. So here you have not, you multiply 6.5 by 2, right? So you end up having 13 O2 molecules, right? 13 multiplied by 2, 26 oxygens. Now, here we go, right? So here we have 10 oxygens, 10 multiplied by 1, and 8 multiplied by 2, 16. 16 plus 10, 26 oxygens. So this equation is balanced. That being said, this presentation is over, and thank you for your attention.